Welcome to our online event, A Modern Perspective on Nuclear Technology. This event is organized by EcoHome, Alliance Green Belarus, and Green Network as part of the series dedicated to 40th anniversary of Chernobyl disaster. My name is Tanya Novikova, and I will be moderating today's discussion. Let me introduce our speaker, Dr. Gordon Edwards. He is president and co-founder of the Canadian Coalition for Nuclear Responsibility. He is a retired professor of math and science from Vanier College in Montreal, and he is expert with more than 45 years of experience working on nuclear energy issues.
Okay, well, thank you very much, everybody, and very much thank you for participating. I'm sorry that this will be all in English. I hope that this is not a problem. I will try to speak as clearly as possible. And if I'm speaking too quickly, I hope the moderator will slow me down a little. We recently formed a group called the Transatlantic Nuclear Free Alliance. This is, excuse me, the date is wrong there. It's April 14th, of course, 2026. And it's about small modular reactors, but also about nuclear power in general. What are the problems of nuclear power, and what are the problems of small modular reactors, as well as what are called advanced nuclear reactors? What are they? Now, one of the things I would point out is that SMR could also stand for spending money recklessly, because as you will see from my presentation, I believe that what this push for small modular reactors is really a fight for survival by the nuclear industry, which has not been doing well in recent decades. Well, going back to my childhood, when I was in high school, nuclear power was presented as almost godlike and a problem-free technology. And of course, we've since then found out that there are many problems which can be very serious with nuclear power. This is a 1972 comic book promoting nuclear power here in Canada by the Canadian Nuclear Society. And now we see the same kind of propaganda, if you want to put it that way, advertising for new nuclear reactors, as if they too have no problems anymore. Suddenly we've magically solved the problems of nuclear waste, of nuclear safety, and of nuclear proliferation of nuclear weapons. This is far from true. Even back in 2019, which is already quite a few years ago, the nuclear industry had already been stagnant for over 25 years. In the first few decades, nuclear power grew rapidly. This is global. These are global numbers. These are numbers from around the world. Nuclear power had an exponential growth, and then it just flattened out. And of course, that was largely coincident with the Chernobyl accident, which is already 40 years ago. So in 1996, for example, there were 438 reactors operating in the world, and it represented 17% of global electricity. In 2019, 25 years later, there were only 4 more reactors, and it represented only 10% of global electricity. And it's still going down. Now it's 9%, and nobody expects it to turn around quickly. So what we have here is a picture of the nuclear industry in rather steep decline in terms of its international importance. Back also in 2019, now the reason I'm mentioning 2019 is that is about the year when small modular reactors began to be talked about widely in the international community. But in 2019, the American Society of Mechanical Engineers wrote that the International Atomic Energy Agency, looking ahead to 2050, sees the most optimistic global electricity market share for nuclear as only about 5%, down from 10% today. And in the United States and Europe, it steadily declines to between 3 and 5% of the market, constituting a potential for market failure. So what we have here is a picture of an industry which is struggling for survival and which is trying desperately to revitalize itself. They knew that they were in problems way back in even 2001 1999 for that matter, the first nuclear renaissance was announced, and it turned out to be a litany of disappointments. At that time, they were hoping that thousands or at least hundreds of new nuclear reactors would be ordered worldwide. These would be the large reactors, and that this would be a revitalization of the industry. But only a handful of orders that came in. And for example, in North America, the first reactors to be given a license to construct in over 30 years after the 3 Mile Island accident in 1979 were 4 nuclear reactors down in the South United States, 2 in Georgia and 2 in South Carolina. Now, the cost of these projects was so enormous that it drove Westinghouse Nuclear into bankruptcy in 2017 because of a $9 billion in losses from the South Carolina projects, which were canceled, even though they had already spent $9 billion. Those losses drove Westinghouse into bankruptcy. The U.S. federal government had given $8.3 billion in loan guarantees on the financing of the 4 reactors. South Carolina abandoned the project. Georgia did not, and those reactors are now operating, but at great expense. In fact, they are considered to be the most expensive electricity anywhere in the world when you take a look at the cost of construction and average it out per megawatt. In Europe, there was a collapse of the French giant Areva based on the Olkiluoto reactor, number 3, which was supposed to be 1,400 megawatts in Finland. It began in 2005. The plan at that time was to have it operational in 3 years, so it should have been operating in 2008 at a cost of 3 billion euros. In actual fact, it started up only in March 2022. That's 19 years later, at a cost of 11 billion euros. So that took 6 times longer to build than promised and cost 4 times more money. This is one of the stars of the nuclear renaissance, but it actually bankrupted Areva. Now, I say bankrupted, of course, being a state-owned corporation, it wasn't really bankrupted. It was just absorbed by the Electricité de France. The actual debt that they incurred, $5 billion in debt, exceeded their entire assets. And that's a definition of bankruptcy. So I want to talk about the nature of the beast. Why is it so difficult for nuclear power to stage a comeback? Why is it so difficult to get these plants built within budget and on time? Well, let's go way back to Henri Becquerel in 1896, who discovered radioactivity. That was the first form of nuclear energy that was discovered. He discovered that uranium rocks containing uranium and thorium, invisible energy was given off ceaselessly. Here's a picture. You can't see radiation, but if you put one of these rocks in a device called a cloud chamber, you can see the tracks of the energy being given off by this rock. And the amazing thing is that this energy has been given off for millions and millions and millions of years without ever stopping. This is radioactivity. It's a form of nuclear energy that cannot be turned off. And that's one of the big reasons why we have a problem with nuclear power. Because radioactivity cannot be turned off, we have to keep it out of the environment of living things for, again, millions and millions and millions of years. That human civilization, of course, is nowhere near that long. And so it becomes an unsolved problem of the human race as to how to protect ourselves against the products of our own creation. Now, the power of the atomic bomb was revealed in 1945, but it was known quite early. Scientists could easily calculate how much energy was being given off for the first few thousand years, and they knew that if all that energy could be released at one time, it would be enormously destructive. And indeed, the destruction of the city of Hiroshima was only due to one uranium bomb. So uranium has this enormous power. Now, we also learned how to harness the power of the atom for peaceful purposes in nuclear reactors. Nuclear reactors are basically a situation of using that energy to boil large amounts of water, creating a great deal of steam, which can be used to spin the blades of a turbine and generate electricity. So just like an oil-fired plant or a coal-fired plant or any thermal plant, it's just another way of boiling water. It's a steam engine. Basically, we're talking here about steam engine technology, which is very inefficient. All steam engines only convert about 1/3 of the raw energy into electricity, and 2/3 of that energy goes into the environment as waste heat. So it's a very wasteful and inefficient process, even if we use such a powerful source of energy as nuclear power. Here is a model of the uranium atom taken by a photograph taken by my friend and colleague, Robert Del Tredici, an award-winning photographer. Uranium turns out to be the key element in all nuclear fission technology. Without uranium, there would be no nuclear weapons of any description and no nuclear reactors of any description. So it is a key element. And the reason is that it's not only radioactive, but it also undergoes something that we discovered in 1938-39. It's called nuclear fission. Nuclear fission occurs when a subatomic projectile called a neutron starts a nuclear chain reaction by splitting a nucleus of a rare form of uranium called uranium-235. That's fissile uranium. Now, that atom splits into two smaller atoms, and energy is released, along with 2 or 3 extra neutrons. And these two smaller atoms are new radioactive materials that were never before seen in nature. They're called fission products. And that's the bulk of the nuclear waste from all nuclear reactors, whether they're large or small, no matter what the coolant is, no matter what the fuel is, you're going to get a large quantity of radioactivity newly made called fission products and other radioactive materials, because the extra neutrons that are given off when fission occurs, they go on to trigger more fissions, but they also go on to produce more radioactive byproducts. Let me explain. What do these extra neutrons do? Well, as I said, they do keep on producing more fission products, and there are hundreds of varieties of fission products, perhaps even 1,000. They also turn some of the uranium atoms into a new material called plutonium and other so-called transuranium elements, such as americium and curium and neptunium and so on. These are elements which are heavier than uranium. Uranium is the heaviest naturally occurring element found in nature, but these heavier elements are created by uranium absorbing neutrons and not splitting, but turning into heavier atoms. In addition, the neutrons activate everything in the core, and I will explain that a little bit. This means that non-radioactive atoms sitting in the core of the reactor, in the steel, in the concrete, in the water, in the air, become radioactive due to neutrons. So first of all, the creation of plutonium, which is very important, it happens when an atom of uranium-238, that's the type that does not undergo a chain reaction. It does not easily undergo nuclear fission, but instead it absorbs a neutron and turns into plutonium. That plutonium can be used to make atomic bombs for thousands of years, because plutonium has a half-life of 24,000 years, much longer than the pyramids of Egypt, which are only 5,000 years old. And that material is a leftover of all nuclear reactors. Regimes thousands of years from now can go and dig up that waste and use that plutonium to build thousands and thousands of nuclear weapons based on that weapons-grade material. Plutonium has become the backbone of the nuclear weapons arsenals in the world today. This is exactly how much plutonium is needed to destroy a city. That's the size of, this is a glass paperweight, but it was manufactured to be the exact size of the ball of plutonium in the Nagasaki bomb. That's how much plutonium you need. Now, even the much more powerful H-bombs, the thermonuclear bombs, which depend upon not only nuclear fission, but also nuclear fusion, they also require plutonium to get them started. That small fission bomb at the top, that's the ball of plutonium at the top there, is needed to raise the temperature to 100 million degrees so that the nuclear fusion can be ignited. Now, I want to now explain a little bit what I meant by activation, neutron activation. When a stray neutron is absorbed by a non-radioactive atom, the result is often a radioactive atom, an activation product. One common example of this is here in Canada, we use heavy water for our moderator in our nuclear reactors, and that's made of a heavy form of hydrogen called deuterium, which is twice as heavy as normal hydrogen, but is not radioactive. However, when it absorbs a neutron, a stray neutron, it becomes radioactive tritium, which is 3 times heavier than normal hydrogen. And that's how radioactive tritium is created in large quantities inside every nuclear reactor, but particularly so in the Canadian reactors. Canadian reactors produce 30 to 100 times more tritium than other light water reactors. So what gets activated? Well, as I just mentioned, water gets activated and produces radioactive tritium. Air is activated and produces radioactive carbon-14. Even the structural materials in the core of the reactor become radioactive waste, dangerous for thousands of years. Steel, concrete, zirconium, and other materials become activated, and so they cannot be recycled but must be stored as radioactive waste forever. So the impurities in the fuel and in the cladding are also activated. This is why nuclear power is sometimes called the ultimate example of the throwaway society, because these wonderful materials, there's some of the best stainless steel in the world, are put into the structure of nuclear reactors. That steel cannot be recycled for any civilian use. It becomes radioactive waste permanently. So that's one of the downsides of nuclear power. Here is how long some of these activation products, there are again dozens and dozens of activation products. These are some of the ones which have long half-lives. You see that these half-lives are tens of thousands of years or hundreds of thousands of years, in some cases even millions of years. The half-life is the time it requires for half of the atoms to disintegrate. It'll still take that much longer for half of what remains to disintegrate. And if you wait for 10 half-lives, that's why I have the 10 half-lives there, the amount of radioactivity will then decrease by a factor of 1,000, but it's still radioactive even after 10 half-lives. So these things it's incomprehensible as to how we're going to keep these things out of the environment of living things for such enormous periods of time. Here's a list of some of the radioactive materials found in all irradiated nuclear fuel. Again, this is from small reactors or large reactors. This is a list of about 211 different radioactive elements, most of them new to the universe, most of them new to the world, only created since 1940, after nuclear fission was discovered. So even this list of 211 isotopes, there we have the transuranic elements, as well as the uranium. The uranium itself, of course, is naturally occurring, but not all the isotopes. Uranium-232 and 233 are not naturally occurring, nor is uranium-236 or 237 or 240. These are newly created isotopes of uranium, and there are newly created isotopes of transuranic elements there too. This list is by no means complete. It comes from Atomic Energy of Canada Limited in a publication from them. Now, we had a Royal Commission of Inquiry into the nuclear waste itself, and this is a graph from that Royal Commission of Inquiry. It was called A Race Against Time, and this came out in 1978, and they pointed out that the time scale at the bottom here goes for 10 million years, and it shows how the blue line, which is the radiotoxicity of 1 year's worth of used nuclear fuel from one reactor. That's just 1 year's worth of fuel from one reactor for a period of 10 million years. And it shows that the toxicity goes down sharply in the first 1,000 years, and then goes down a little more slowly up until about 10,000 years. And then it starts going back up again. The toxicity actually increases after about 10,000 years being stored. And that's because of changes that occur in the radioactivity as it decays. Because when a radioactive atom disintegrates, it doesn't just disappear. It changes into something else, which can also be radioactive. I mentioned that plutonium, for example, has a 24,000-year half-life. But when plutonium atoms disintegrate, they turn into another type of radioactive atom, which has a half-life of 700 million years. So that's why the longevity is so very long. Now, the second nuclear renaissance, the first nuclear renaissance was a big disappointment. The second nuclear renaissance began around 2018, 2019 with these so-called small modular reactors. Now, despite the fact that this was already 7 years ago, 8 years ago now, there has not been a single small modular reactor built anywhere in the Western world. There have been 2 small modular reactors built by Russia, and there have been one built by China, but there have been none built in the Western world. The rationale for small modular nuclear reactors was that large reactors are too expensive and maybe the small ones would be more affordable. Large reactors are too powerful for some small grids. Maybe the small ones would fit in better. SMRs can be modular for mass production. SMRs can deliver heat as well as electricity, and that can store that heat to make the usage of the plant more flexible. Of course, that could also be done with large reactors as well. So there's nothing special in that regard for small modular reactors. It's also often stated that small modular reactors can serve as backups for renewable energy, which is a variable form of energy because the sun does not always shine and the wind does not always blow. Well, the actual fact of the matter is that none of these have been built yet. They're all first of a kind, and therefore they tend to be very speculative. The problems for small modular reactors is that they're very costly power. Mass production is absolutely needed in order to bring the price down, because when you build a plant which is only 1/3 as powerful, it doesn't take only 1/3 the cost. It might take half the cost to build a plant which is only 1/3 as powerful. That means the cost for the electricity you're producing is more expensive, not less. Also, because it is smaller, the fission products and the activation products, these radioactive materials, are more concentrated. They're more concentrated, and thus per kilogram, the waste materials are more radioactive. There's also less of a massive containment, and this is one of the reasons why they want to go underground, because with less massive containment, they're more vulnerable to attack, to military attack, to unpredictable weather events, which are particularly powerful, and to such as the tsunami that brought down the Fukushima reactors in Japan. And also there's over 130 different models of small modular reactors. There's so much competition that it's not justified to move to mass production. And without mass production, you cannot bring the costs down. Private funding is also hard to find. So therefore, public money is needed. And our experience in North America has been that all of these small modular reactors that they have talked about have required public money and have attracted very little or no private money. The problem is there's a lack of markets and very slow deployment. So here's an example, the NuScale pressurized water reactor. Now this was developed going way back to the 1999s, but it wasn't really announced as a project until 2015. 2015, of course, is a long time ago. And that project went ahead for a number of years and was canceled in 2023. It was canceled completely. And the reason why is because the cost of the project, the estimated cost, had almost tripled. It had increased to 250% of the original cost estimate. And so the municipalities that wanted to buy this power simply canceled their orders, and this project never went ahead. Here's an example from Canada, the ultra-safe micromodular reactor. It was supposed to be a gas-cooled 5 megawatt reactor with a molten salt heat storage system. Ultrasafe filed for bankruptcy in 2024, even though it had already been announced as being a project in Canada to be built at Chalk River, the home of Atomic Energy of Canada Limited. And the project has not been outright canceled, but paused. They're waiting to find somebody who will be willing to take over the bankrupt corporation. It's intended for the Chalk River site in Ontario, as I said. So there's a bankruptcy there. Now here's the BWRX 300, an artist's conception, which is actually under construction. They're digging the hole as we speak. It's a boiling water reactor, 300 megawatts, estimated to cost $6.5 billion in Canadian money. That's equal to the cost per megawatt of the Volto plants in Alabama that I mentioned to you earlier. So there has been no saving as a result of the smaller size. It has been as expensive as the most expensive project ever built in North America. The Canadian regulator, CNSC, has given a construction license for the first of 4 units to be built east of Toronto at a site where there are large nuclear reactors at Darlington. Now, this is not exactly a small reactor when you look at it more closely, because it's 21 stories high. The 10 stories above ground are balanced by another 11 stories below ground. So it's not so small, and it's not modular either. You can't mass produce these items because you only have first of a kind reactor. These have to be done individually. And a workforce of up to 4,000 has been cited by the Prime Minister, who has invested federal money into this project to the tune of almost $3 billion. So already this has been subsidized by almost $3 billion of Canadian taxpayers' money in order to see it to its completion. Of course, the $6.5 billion is only an initial cost estimate. We fully expect that the cost will be greater than that when it's finally built. How much greater, we don't know. But it's very difficult to depend upon initial cost estimates. The BWX is a simplification of an earlier model, which was licensed in 2011. It's called the Economic Boiling Water Reactor. The BWRX 300 is 90% smaller in volume, and part of the smallness has been achieved by eliminating a number of safety systems, including a core catcher to prevent melt through at the bottom of the reactor in case the core melts, including the emergency core cooling system, which has been eliminated, including the high pressure relief valves on the reactor vessel itself. These have been eliminated as well. So they're depending upon passive containment cooling. But that passive containment cooling depends upon valves opening and closing faithfully. And those valves which are opening and closing, they don't always work. They have a history of problems too. In fact, the 3 Mile Island accident in Pennsylvania in the United States back in 1979 was totally caused by 2 valve failures. One valve failure that was mechanical, and one valve failure that was simply a valve that failed to close when it should have. It was a pressure relief valve. And that's what caused the meltdown at 3 Mile Island. So depending on valves can be dangerous too. So nuclear fission reactors have a number of problems. Problem number 1 is the nuclear waste. Problem number 2, nuclear catastrophes, nuclear disasters, nuclear accidents like the Chernobyl accident. Now, problem number 3 is nuclear decommissioning, taking apart the radioactive structures, which, as I mentioned to you, is going to be an expensive job, and those wastes are going to have to be stored as radioactive waste as well. And problem number 4, spreading nuclear weapons by the creation of plutonium and other weapons usable materials. None of these problems is eliminated by the use of smaller reactors. All of those problems remain. The nuclear waste is fundamental. You can't get rid of it. There it is. Nuclear catastrophe simply means anything that will release the radioactive inventory to the environment. For example, we've seen in Ukraine, we've seen how the war threatens the Zaporizhzhia nuclear power plant. Well, just because of military operations, that can happen with small modular reactors too. And small modular reactors are even less able to resist powerful bombing or powerful outside forces. Nuclear decommissioning remains the same, and spreading nuclear weapons remains the same as well. I want to say a word about the competition. Why is it that nuclear power is having so much trouble staging a renaissance, staging a revitalization? And the problem is the competition is too strong. The status of renewable energy has been improving year by year. The price of renewables keep going down. The price of nuclear keeps going up. Even the price of batteries and battery storage of energy and other forms of storage of energy are also going down. So the poor nuclear guys have to compete against competitors, solar plus storage and wind plus storage, even at the most expensive edge of the estimates. This is from Wall Street, a firm called Lazard, who gives graphs on the levelized cost of energy to compare different energy options. Even the greatest cost of solar plus storage and wind plus storage is smaller than the smallest cost of nuclear. So this is a very bad competition for nuclear. They have to convince people to spend 3 times or 4 times as much money for the same energy they could have got from solar energy or from wind energy. At the same time, it is, by the way, that graph was in 2023, but here's the graph from 2025. Things have not changed markedly. Solar plus storage and wind plus storage is so much cheaper than nuclear. And in fact, it has been growing by leaps and bounds around the world, far faster. Now, I mentioned batteries. People have no idea how much improvement has been going into these utility scale batteries. This is a study from Texas. Texas has invested a lot of money in solar energy and also in storage. Now, the instant battery discharge reached almost 10 gigawatts. These are from batteries, 10 gigawatts of power from batteries on ERCOT's electrical grid in Texas in December 2025. Now, that's equivalent to 10 large nuclear reactors. So these batteries can store an enormous amount of energy, and the problems of the intermittency or the variability of wind and solar are rapidly being solved. And what's even better is that the price keeps going down. Now, here's a graph from years ago. I won't bother belaboring it. The green line is renewables. This is projected by the U.S. Energy Information Administration. And you see nuclear at the bottom. Even under the most optimistic scenario, it grows very, very slowly, if at all. They talk about tripling nuclear by 2050 at COP28, but they also talked about tripling renewables by 2030. So you could triple renewables 20 years earlier than you can possibly triple nuclear. That's another advantage of the renewables. They're much faster to build, much faster to deploy. They pay themselves back much faster, and that means the money can be reinvested in more of the same. With nuclear, it costs more, it's slower, and even when you get the returns on the investment, you have to put a large chunk of that aside to deal with the waste problems and the decommissioning problems. So as I said, COP28, over 200 nations pledged to triple renewables and double energy efficiency by 2030. There were only 25 nations who unofficially got together and said that they wanted to triple nuclear power by 2050. That was not, however, an official position of the COP28 conference. People say, well, if you don't have nuclear, aren't you going to worsen the greenhouse gas problem? Well, Germany, of course, as you know, they closed down all 17 of their nuclear reactors on schedule after vowing to do so years ago. And during that whole period of time, they have been reducing their greenhouse gas emissions, as shown in this graph here. And in fact, the total emissions are down by 30%, greenhouse gas emissions from Germany over this period of time. And in the energy sector, the reduction in greenhouse gases has been about 50%. So we can see that without nuclear, greenhouse gas reduction continues with renewables. Renewables do an even better job of reducing the greenhouse gases more quickly. I just want to make a final word, and that is that I do believe that we as a society have to really be cautious not to be fooled by overly optimistic cost estimates, which turn out not to be true, overly optimistic performance promises, which turn out not to be true, because these things, unlike the renewables, these things are unproven. None of these things have been built yet. And there's always been, historically, cost overruns and construction delays, as well as, in some cases, simple failures. Thank you.
You already answered my questions. I wanted to ask you as a moderator, what are alternatives to nuclear energy, because we were told by politicians and by corporations that there is no other alternative because our demand is growing up because of artificial intelligence. But your argument that renewable energy is growing much faster and it is generating more power right now than nuclear energy. It is pretty convincing. And second question I had was about small modular reactors, and now we can see that there is no reliable technology yet. My question to you would be, what do you think about the culture? Because another argument in favor of nuclear energy would be that safety culture now is much different than safety culture 40 years, 30 years ago.
The thing about renewables is you don't need to have much of a safety culture because nothing terribly can happen to them, even if they're bombed. I mean, it's going to destroy the facility, but it's not going to cause a disaster. But no matter what the safety culture is, when you think about the Fukushima reactor accident, Japan was known to have a very high level of safety culture, manufacturing skill and operational skill. And yet, look what happened, you know? So some of these accidents that occur in the United States, the 3 Mile Island accident in Pennsylvania is another example. No matter what the plans are, no matter what the safety culture is, there's something fundamentally problematic about nuclear. And that is that if the fuel overheats and if the radioactivity is released into the environment, then you have a disaster. And that can happen by ways which cannot always be foreseen. In fact, my contention is that every single example of a major nuclear accident that has occurred so far was completely unforeseen before it happened. So when we talk about the probability of an accident, I'm a mathematician by training. I teach probability. And by definition, those accidents had probability 0 before they happened. The reason they had probability 0 was because they were not even considered possible. First of all, I think that nuclear power's great attraction is the enormous concentration of energy. It's the most concentrated form of energy that you can find, because the force that holds the nucleus of an atom together is the strongest force in the universe. And so it's very hard to turn your back on the strongest force in the universe. And so the attraction is the concentration of energy, and of course the fact that while it's producing the electricity, at that moment it's not generating greenhouse gases. Of course, there's a lot of greenhouse gases that goes into mining the uranium, enriching the uranium, building the reactor, and so on, and also taking it apart again. The disadvantage, however, is the creation of hundreds, literally hundreds of radioactive materials, which the Earth had not seen before 1940. So these wastes are only not even as old as I am. I happen to be born in 1940. These wastes are much younger than me. And I believe that any technology which mass produces such dangerous poisons already should be suspect. We talk about accidents. We talk about accidental crashes of airplanes, for example, or accidental meltdowns caused by carelessness or by external forces. It can also be caused by malicious actions. And the malice of human beings, when it's unleashed, can be really devastating. You can imagine if an enemy is sufficiently ruthless, they would not hesitate to bomb nuclear reactors. And these small reactors by the very fact of making them smaller, we've made them more vulnerable. And they're easier targets than the larger ones, which did have thick concrete walls, which were able to resist a lot of external forces. The renewables are really undergoing a renaissance. They truly are. They're zooming, growing very rapidly worldwide. And as the price of storage keeps dropping, I think that this question about variability is going to become a question of the past. Right now, it's understandable that people are worried about it, but the utility scale batteries and other storage methods, Finland has developed something called a sand battery, which I could talk about if people are interested, not for electricity, but for heat, for district heating. I do have to give credit to the nuclear industry. They have expended enormous ingenuity on safety matters. They've always taken safety very seriously. It's simply sometimes a little too difficult to anticipate every single thing that can go wrong. And the 3 Mile Island accident is a case in point. There was one valve that was less closed mechanically that should not have been closed. And that caused the dry out of the steam generator and the overheating of the core of the reactor. That problem was fixed within 2 minutes, and everything should have gone back to normal. The only problem there was another valve inside the reactor that stuck open and caused a loss of coolant, which led to the meltdown, which led to the melting of the reactor core. And nobody knew that that valve was stuck open for more than 2 days. So for 2 days, nobody realized what was happening with the reactor. You can't go in there because the radiation fields are so intense that they will kill any human being that comes close. The result is you have to depend upon instruments. Everything has to be done by remote control, and you can't send men in to directly inspect it. They will simply die.
Okay, so I will ask my second question. Gordon, we have right now, we have the situation of war, like a Russian aggression in Ukraine. We have also in United States war against Iran. In what way contemporary nuclear power plants are protected against airstrikes, against attacks?
In 1976 in Britain, there was a Royal Commission report authored by a nuclear physicist, Sir Brian Flowers, and it's called the Flowers Report. He pointed out that if nuclear power had been developed before World War II, then large parts of Europe would today be uninhabitable because of World War II, because those plants would have definitely been targeted during the war. And by sabotage, by bombing, by so on, conventional war. And that would have released all of the radioactive contents of those reactors and created a terrible wasteland. So that's a problem with nuclear power, which does not exist with renewables. And we've seen the Zaporizhzhia plants, even those reactors with the thick walls, they still are vulnerable. And of course, sabotage is another possibility. If somebody infiltrates the plant and sabotages it from within, then they can cause the release of all these radioactive poisons into the environment. So this is the big problem, the biggest problem with nuclear power. I think it's very revealing that when they talk about SMR, they leave out the N, because it should be SMNR, small modular nuclear reactors. They leave out the N on purpose because that's where all the problems are. In fact, small is debatable. They're not really that small when you, as I showed you with the BWRX 300, 21 stories high. They're not really modular. They're hoping that they can become modular, but they're not yet modular. The only thing that they are, undeniably, is nuclear. And the nuclear is where all the problems lie. That's what drives the cost upwards. The reason why the cost keeps going higher is because they can't afford to take chances. They can't afford. They have to spend more money on more safety systems and to meet certain possibilities, scenarios that are identified by smart people. So nuclear energy is fighting an uphill battle, even if it was truly affordable, even if it was truly competitive with renewables and with fossil fuels, even so, it would be a tough sell. And yet, I mentioned to you how the market flattened out for the last 25 years. It was an absolutely flat market. There was nothing happening, very little. Even in China today, last year, for example, they started operation of 2 new nuclear reactors, and they're building more. But they're deploying renewables at a rate 10 times, even 100 times faster than they're deploying nuclear. And so, for example, whereas they deploy 5 gigawatts of nuclear, they have 500 gigawatts of renewables. So China itself is showing the way that they see that the most advantageous energy policy for them is to go that route.
You already answered my questions. I wanted to ask you as a moderator, what are alternatives to nuclear energy? Because we were told by politicians and by corporations that there is no other alternative because our demand is growing up because of artificial intelligence. But your argument that renewable energy is growing much faster and it is generating more power right now than nuclear energy. It is pretty convincing. And second question I had was about small modular reactors, and now we can see that there is no reliable technology yet. My question to you would be, what do you think about the culture? Because another argument in favor of nuclear energy would be that safety culture now is much different than safety culture 40 years, 30 years ago.
The thing about renewables is you don't need to have much of a safety culture because nothing terribly can happen to them. Even if they're bombed, I mean, it's going to destroy the facility, but it's not going to cause a disaster. But no matter what the safety culture is, when you think about the Fukushima reactor accident, Japan was known to have a very high level of safety culture, manufacturing skill and operational skill. And yet, look what happened, you know? So some of these accidents that occur in the United States, the 3 Mile Island accident in Pennsylvania is another example. No matter what the plans are, no matter what the safety culture is, there's something fundamentally problematic about nuclear. And that is that if the fuel overheats and if the radioactivity is released into the environment, then you have a disaster. And that can happen by ways which cannot always be foreseen. In fact, my contention is that every single example of a major nuclear accident that has occurred so far was completely unforeseen before it happened. So when we talk about the probability of an accident, I'm a mathematician by training. I teach probability. And by definition, those accidents had probability 0 before they happened. The reason they had probability 0 was because they were not even considered possible. First of all, I think that nuclear power's great attraction is the enormous concentration of energy. It's the most concentrated form of energy that you can find because the force that holds the nucleus of an atom together is the strongest force in the universe. And so it's very hard to turn your back on the strongest force in the universe. And so the attraction is the concentration of energy and, of course, the fact that while it's producing the electricity, at that moment, it's not generating greenhouse gases. Of course, there's a lot of greenhouse gases that goes into mining the uranium, enriching the uranium, building the reactor, and so on, and also taking it apart again. The disadvantage, however, is the creation of hundreds, literally hundreds of radioactive materials, which the Earth had not seen before 1940. So these wastes are only not even as old as I am. I happen to be born in 1940. These wastes are much younger than me. And I believe that any technology which mass produces such dangerous poisons already should be suspect. We talk about accidents. We talk about accidental crashes of airplanes, for example, or accident meltdowns caused by carelessness or by external forces. It can also be caused by malicious actions. And the malice of human beings, when it's unleashed, can be really devastating. You can imagine if an enemy is sufficiently ruthless, they would not hesitate to bomb nuclear reactors. And these small reactors, by the very fact of making them smaller, we've made them more vulnerable. And they're easier targets than the larger ones, which did have thick concrete walls, which were able to resist a lot of external forces. The renewables are really undergoing a renaissance. They truly are. They're zooming, growing very rapidly worldwide. And as the price of storage keeps dropping, I think that this question about variability is going to become a question of the past. Right now, it's understandable that people are worried about it, but the utility scale batteries and other storage methods, Finland has developed something called a sand battery, which I could talk about if people are interested, not for electricity, but for heat, for district heating. I do have to give credit to the nuclear industry. They have expended enormous ingenuity on safety matters. They've always taken safety very seriously. It's simply sometimes a little too difficult to anticipate every single thing that can go wrong. And the 3 Mile Island accident is a case in point. There was one valve that was closed mechanically that should not have been closed. And that caused the dry out of the steam generator and the overheating of the core of the reactor. That problem was fixed within 2 minutes, and everything should have gone back to normal. The only problem there was another valve inside the reactor that stuck open and caused a loss of coolant, which led to the meltdown, which led to the melting of the reactor core. And nobody knew that valve was stuck open for more than 2 days. So for 2 days, nobody realized what was happening with the reactor. You can't go in there because the radiation fields are so intense that they will kill any human being that comes close. The result is you have to depend upon instruments. Everything has to be done by remote control, and you can't send men in to directly inspect it. They will simply die.
Okay, so I will ask my second question. Gordon, we have the situation of war, like a Russian aggression in Ukraine. We have also and United States war against Iran. In what way contemporary nuclear power plants are protected against airstrikes, against attacks?
In 1976 in Britain, there was a Royal Commission report authored by a nuclear physicist, Sir Brian Flowers, and it's called the Flowers Report. He pointed out that if nuclear power had been developed before World War II, then large parts of Europe would today be uninhabitable because of World War II, because those plants would have definitely been targeted during the war, and by sabotage, by bombing, by so on, conventional war. And that would have released all of the radioactive contents of those reactors and created a terrible wasteland. So that's a problem with nuclear power, which does not exist with renewables. And we've seen the Zaporizhzhia plants, even those reactors with the thick walls, they still are vulnerable. And of course, sabotage is another possibility. If somebody infiltrates the plant and sabotages it from within, then they can cause the release of all these radioactive poisons into the environment. So this is the big problem, the biggest problem with nuclear power. I think it's very revealing that when they talk about SMR, they leave out the N, because it should be SMNR, small modular nuclear reactors. They leave out the N on purpose because that's where all the problems are. In fact, small is debatable. They're not really that small. When you, as I showed you with the BWRX-300, 21 stories high, they're not really modular. They're hoping that they can become modular, but they're not yet modular. The only thing that they are, undeniably, is nuclear. And the nuclear is where all the problems lie. That's what drives the cost upwards. The reason why the cost keeps going higher is because they can't afford to take chances. They can't afford. They have to spend more money on more safety systems and to meet certain possibilities. scenarios that are identified by smart people. So nuclear energy is fighting an uphill battle, even if it was truly affordable, even if it was truly competitive with renewables and with fossil fuels. Even so, it would be a tough sell. And yet, I mentioned to you how the market flattened out for the last 25 years. It was an absolutely flat market. There was nothing happening, very little. Even in China today, last year, for example, they started operation of 2 new nuclear reactors, and they're building more. But they're deploying renewables at a rate 10 times, even 100 times faster than they're deploying nuclear. And so, for example, whereas they deploy 5 gigawatts of nuclear, they have 500 gigawatts of renewables. So China itself is showing the way that they see that the most advantageous energy policy for them is to go that route.
We have some more questions for you. One would be about the same small modular reactors. Compare, please, the decommission process of small modular reactors in traditional big nuclear power plants. How much time, money, and human power they demand comparatively?
Small modular reactors are going to have much more activation radiation in the structural materials. In other words, the reactors themselves are going to become a lot more radioactive than the large reactors per kilogram. And the reason for that is that because the reactors are smaller and the core is smaller, therefore the structural materials are much closer to the core, and consequently they get much more irradiated by those stray neutrons. And so there is a stronger buildup of radioactive activation products. So the decommissioning is going to be more difficult for the workers than for the large reactors. Already it's difficult for the large reactors. In Canada, for example, they won't even begin to think about decommissioning a large reactor until after waiting for about 40 years. And that's because the gamma radiation fields are so high for the workers that they can diminish greatly. One of the worst culprits in this situation is cobalt-60. Cobalt-60 is a very strong penetrating radiation emitter, gamma radiation, and it only has a 5.7-year half-life. And so if you wait for 40 years, a good deal of it has gone away. So it's been reduced by a couple of orders of magnitude, and that's why they wait. Well, with the small reactors, it's going to be a problem. They often talk about putting small reactors in remote locations. Well, moving the material into those small locations is a lot easier than moving the waste out, because the waste requires very heavy shielding. We have, for example, just to use Canada as an example again, when we put our nuclear waste into dry storage, the storage container is 60 tons, whereas the waste itself is only 10 tons. So imagine a refrigerator, for example, having a storage container which is 6 times bigger than the refrigerator itself. Well, that's what we're doing with our high-level waste. And that's simply to cut down on the external gamma radiation exposures. So it's going to be a lot more difficult to move these wastes out of the site where the reactor was built than to build the reactor in the first place. So the problem with nuclear is you can't afford to just think about it as an investment at the front end. You have to think about all the investments that are going to come afterwards. It's really the only form of energy that I know of which has a very high capital cost at both ends, both at the front end and at the back end.
Thank you for answering this question. We have another one which is about waste from renewables, because this is another argument that renewable energy, for example, if we will talk about lithium, about mining of all the rare earth elements, if we compare the waste from nuclear energy and from nuclear reactors, even small modular and renewables, what would you say? Can we even compare these things?
Yes, well, that's a very good point, and it's a very good question. Renewables, in fact, do deal with dangerous materials, rare earths, etc. Rare earth mining is very dangerous. It is, by the way, rare earths, when found in nature, geologically, they're often associated with uranium and thorium deposits too. So the miners who mine the rare earths are not only dealing with toxic materials in the rare earths, but also with the radiotoxic uranium and thorium as well. So there are radiological dangers in mining the rare earths too. However, when it comes to renewables, these dangerous materials were not created by the renewable energy. In the nuclear power plant, the wastes are created by the nuclear reactor. The wastes that come out of the nuclear reactor were never there when you built the reactor. They have been created by the process of nuclear fission. In fact, nuclear power is the only technology in the world that actually creates new elements, new toxic elements. In the case of the dangerous materials used in renewables, they come from nature and they can be recycled and reused, whereas the waste from nuclear plants cannot be reused. They have to be treated as radioactive waste. They have to be stored and buried. They cannot be recycled into civilian use. So there's a big difference in my mind. However, that is not to say that there aren't serious problems in the renewable scenario. It is true. There's serious problems with every energy scenario. You can't think of any energy scenario that does not have environmental problems. But it does not leave a toxic legacy for millions of years. The dangerous materials associated with renewables came from the earth and can be recycled. The dangerous materials that are for nuclear power are created in the nuclear reactor and cannot be recycled.
Thank you so much. And we have another question. More and more countries in Europe declare that they want small nuclear modular reactors. What do you think why this happens?
Well, it's because of a lot of money being spent by the nuclear industry and by the governments which promote the sale of nuclear reactors, such as my own government, the Canadian government, to convince others that this is the way to go. So there has been a great selling job. It's the same story that we heard when I was in high school. I was told that nuclear energy is safe, clean, and inexhaustible, and I was in favor of it. It sounded great. Who could possibly be against something that sounds so wonderful? Now, similarly, people are now being told once again that these small modular reactors are somehow clean. They're not clean. To describe nuclear energy as clean is a misnomer. Not only do they produce high-level radioactive waste, but they also give off routine emissions of radioactive tritium and carbon-14 and iodine-131 and much smaller amounts of many other particulates, radioactive particulates, all of which are cancer-causing agents into the environment. To call this clean is ridiculous. On the other hand, renewables genuinely are clean in their operation. They do not give off such emissions at all. I'm not trying to say that it's problem-free. There's definitely problems associated with all of them. I would also like to point out the renewables are not limited to solar and wind. There are many other varieties of renewables. They've talked about wave power. They've investigated wave power in England, tidal power. They've even talked about ocean thermal power. And of course, the big target for the future, I believe, is going to be harnessing geothermal energy in an efficient way. If we can master the technology of deep drilling to get down to closer to the Earth's core, where we can truly have a closed system, a closed loop system of sending water down and back up again to generate electricity for using geothermal energy, this will be a non-variable, truly inexhaustible in human terms source of energy. So you might say that solar and wind are simply the appetizers for a kind of a larger diet of renewable energy sources.
Thank you again for your reply. We have another hand, and I will give them the floor.
Yeah, thank you. Thank you for the presentation. But I would like to say about, for example, fast reactors and thorium reactors, so that I think it's more important today. It's more important, more perspective maybe technology, and from another side, I can see that only Russia and only China is make some progress in this technology. And what do you think about it? Maybe in the future it will be it's possible that this technology will be more perspective now, and in the future we can face with a situation when only Russia and China can produce new technology.
Yes, fast reactors was exactly where I broke off my presentation. I was going to talk about fast reactors. One of the reasons why they use other coolants, they use molten salt or liquid sodium, liquid metal as coolants, is because they do not slow the neutrons down the way water does. They're called slow reactors for that reason. If you use other coolants that are transparent to neutrons, more transparent, such as molten salt or liquid metal, then you can have fast reactors. And this creates more fission. And you mentioned thorium as a fuel. Of course, the ironic thing about thorium is that while it's 3 times more abundant than uranium, and therefore, and is also a primordial radioactive element in the Earth's crust, it's always been there from the formation of the Earth. It's not really a fuel in the same sense that uranium is. You cannot fuel a reactor with thorium. What you can do is you can mix the thorium with another material, which is a fuel, such as highly enriched, or well, enriched uranium or plutonium. And if you put that mixture into a reactor, then the fuel will produce extra neutrons. And the extra neutrons will turn some of the thorium into a new isotope of uranium called uranium-233. And that's the fuel that we talk about. That's the fuel that comes out of the thorium cycle. So thorium is not a fuel, but it is what's called a fertile material that breeds uranium-233, an isotope of uranium that's not found in nature. And that is a very powerful fuel and also a very powerful nuclear explosive. And in fact, the first motivation for using thorium way back in 1947 here in Canada, we had a reactor that used thorium rods at the invitation of the U.S. military, because they were very interested in getting uranium-233 for bombs. They did detonate a bomb using uranium-233 down in the Nevada test site to demonstrate its power. When U-233 is created, it is 100% enriched, unlike natural uranium, which is only 0.7% enriched. Nowadays, when we use our reactors, we have to enrich the uranium to a high degree, the kind of thing that Iran is being bombed for right now. The reason why, the ostensible reason, the declared reason for attacking Iran, although there are many undeclared reasons as well, but the declared reason is to prevent them from having weapons-grade highly enriched uranium more than 90% enriched. Well, uranium-233 is 100% enriched when it's created. So there are problems with the thorium reactor and these other models that people are unaware of or haven't thought sufficiently about. None of those reactors make sense unless you have something called reprocessing. Reprocessing, which the industry calls recycling, but that's a misnomer. Reprocessing is a way of taking the used nuclear fuel, which is already enormously radioactive, containing all that inventory of radioactive, newly created radioactive materials, and destroying the fuel assembly in order to get the plutonium or the uranium-233 out of the fuel. In order to get the useful material, the fuel material, the plutonium or the uranium-233, you have to destroy the fuel bundles. When you destroy the fuel bundles, you liberate all of the radioactive contents. And this creates an enormous mess, because this is now much more difficult to handle than the solid fuel bundles were. And as a result, when you look at the places where reprocessing has taken place on Earth, they are among the most contaminated sites, radioactively contaminated sites in the world. At Hanford, Washington, for example, they did reprocessing to get plutonium for bombs, and then subsequently they did reprocessing for civilian purposes as well. The cleanup of that site is estimated by the US Government Auditing Office as between $300 billion and $640 billion. Those are American dollars. Imagine between $300 billion and $640 billion cleanup. If you look at Sellafield in northern England, where they did reprocessing there, you'll find that there's a tremendous cleanup cost there that keeps going up and up and up year by year as they discover more and more complexities. Mayak in Russia was the site of reprocessing in Russia. When you look at these places, you realize there's an enormous legacy of radioactive contamination behind. You may know about the fact that there's a huge tract of land in northeast of Mayak, the Mayak reprocessing plant, which has been off limits to humans since 1957, when one of the waste tanks exploded and contaminated a very large area. So reprocessing is a very dangerous operation, and it is inseparable from the efficient operation of these fast reactors. So the fast reactors, they always sound good when you only look at the front end. It's only when you look at the back end that you realize that you're buying into something which is far more dangerous than it appears to be when you only look at the facade.
Thank you so much. I believe we don't have more questions for you, and thank you again for your presentation and for this explanation what nuclear energy is at the moment and what small modular reactors are.
When you take a look at the longer picture, the longer view of things, you realize that nuclear power does provide a very powerful centralized source of energy that can be quite useful for any industrial country or non-industrial country even. But it does leave a legacy which is millions and millions of years of problems. For example, you might say that the product of a nuclear power plant is electricity, but I say electricity is only a temporary blip on the screen. It's only a few decades of electricity. What you're really producing when you have a nuclear power plant is millions of years worth of radioactive waste and tens of thousands of years worth of weapons usable plutonium. So you're creating headaches for future generations that will not get the benefits from that reactor at all, but will get all the headaches. The other thing I'd like to mention is that when you think about renewable energy and think about it as a more and more appealing and practical alternative, despite its problems, which do exist, but when you look at the whole promise of a renewable future, a renewable energy future, you realize that many of the crises in the world today would not occur if we were based on renewable energy. The Strait of Hormuz, the blockage of the Strait of Hormuz wouldn't matter because we're not exporting sunbeams, we're not exporting wind, we're exporting fossil fuels. Right now, we have a shortage of enriched uranium in both the United States and France. Two, you might say, nuclear power superpowers. They have the most nuclear reactors of any country, and yet they don't have enough enriched uranium for their own needs. Guess where they're getting some of their enriched uranium from? Russia. Despite the embargo on Russia, despite the Russia-Ukraine war, they are forced to buy enriched uranium from Russia because they don't have enough for themselves. Now, that's going to be corrected. They're going to build more enrichment plants. But I'm just saying, not only are there environmental benefits and financial benefits, economic benefits to renewable energy, but there are also geopolitical benefits as well. Thank you.